In the beginning, there was nothing. Then at time zero, about 12,000 million years ago, the universe was born in a searing hot fireball called the Big Bang. In the earliest moments of the Big Bang, the stuff of the universe was unimaginably hot, a seething cauldron of electromagnetic radiation and microscopic particles. As the fireball expanded, the building blocks of all ordinary matter started to form. Atoms jammed together. Matter collected into clumps. From these clumps, the early stars were formed. Deep within them, the fury of nuclear fire began. Millions and millions of tons of hydrogen fused into helium. Energy burst outwards to form blazing suns. Stars smashed together. Stars exploded. Billions of stars moved towards common centers where gravity dominated their every move. They began to wheel about those centers to create the cities of stars, the galaxies. Still creation marched on. Material ejected by exploding stars settled into cold bodies, circling around newborn stars. This was the beginning of planets and moons. Just over 4,000 million years ago, around a very average star in a very insignificant part of the universe, our solar system was formed. This could all be science fiction. So why have scientists come to believe such a bizarre idea? The deep exploration of space allows us to see far back in space and time. The Hubble telescope is built to see 12,000 million miles across the universe. In many ways, it's like a time machine. This picture was taken by the Hubble telescope. It shows many distant stars and galaxies, but we're not seeing the universe as it is today. Astronomers believe it's a picture of the universe as it was 5,000 to 7,000 million years ago. Light travels at 186,000 miles a second. But even at this incredibly high speed, it will take light millions of years to reach our eyes from some of the far-flung corners of the universe. So many of these images are pictures of the universe as it existed before the Earth was formed. The deeper Hubble looks into space, the further back in time it sees, and the closer it approaches the events that followed the Big Bang, the very origin of the universe. The stars are the powerhouses of the universe. How they work and how they formed is crucial to understanding how the universe was born. The Sun is our nearest star. It holds the key to unraveling the secrets of all the stars.
The three reasons why we'd like to study the Sun are, firstly, its effects on the Earth. It affects us directly, so we want to understand that. There are huge explosions called solar flares that occur in the Sun's atmosphere that can send streams of highly energetic particles into space. And we see the aurora borealis, the aurora australis. Those are the more beautiful effects of these things. Secondly, it provides us with an atomic physics laboratory. We can see gases in the Sun's atmosphere that can't be recreated on Earth. And thirdly, it provides us a view, if you like, a window into the rest of the universe, because the Sun is a star and we can study the processes on that star. The Sun is a very hot ball of gas, and as with all hot objects, it radiates, it glows. And most of the radiation is in the form of visible light, the light that we can see.
We can learn a lot about the sun just from its visible light.
We can discover how the sun works by finding out what it's made of, and to do that we need to analyse the light. Now normally to analyse the light from a star you need a large telescope like this one at the University of London Observatory. Now the sun is far from being a faint star. In fact, it's so bright that if you were to look at it with your eyes, well goodness, a telescope like this, you'd certainly do a lot of damage. What we can do, because the sun is bright enough, is just point this telescope at the daylight sky, because there's plenty of sunlight around. Once we've collected that light, we can pass it through a variety of instruments, or something called a spectrograph, and that has in it either a grating or a prism, which will split up the white sunlight into lots of different colours, and then we can have a look at those to see what the sun's made of.
When ordinary white light passes through a prism, it's split up into its colours to produce a spectrum. If white light is passed through this special slide called a diffraction grating, a spectrum is produced again. If we look at neon light through a diffraction grating, we don't get a continuous spectrum. It's made up of lines. This line spectrum is neon's fingerprint. Other elements like hydrogen and helium have their own characteristic set of lines, which are different from neon's. We can identify all elements from their line spectra.
When we split the white light up from the sun, we find that it creates all these colours, and on top of these colours there seems to be numerous dark lines. These lines are like fingerprints, and they tell us what elements and molecules are in the sun. I can see a line near the red end of this spectrum which I know corresponds to hydrogen, so I know there's hydrogen in the sun. Over in the blue end of the spectrum I can see two very deep lines which I know are calcium lines. So we've got hydrogen and calcium in the sun, and numerous other lines which I know correspond to things like iron, silicon and oxygen. From information such as this, astronomers can tell that the sun is basically a very large ball of gas, mostly hydrogen.
Hydrogen is the simplest and most abundant element in the universe. It was the first element to be produced after